In this screencast, we want to perform an LU decomposition of two matrices. First, a 2 by 2 matrix and a 3 by 3 matrix. And the goal is to separate, in the case of 2 by 2, to break this into an upper and lower diagonal matrix, such that the product of these two matrices will return the original matrix A. The upper diagonal matrix has this form, where we're trying to identify three constants with a 0 in the lower left corner, and the lower diagonal matrix, we've got one unknown with 1s on the diagonal. In this 3 by 3, again, we've got these 6 unknowns for the upper diagonal and these 3 unknowns for the lower diagonal. So we want to explore an algorithm for going about this for both matrices, and moreover we want to figure out how the number of computations will scale with the size of the matrix. So in other words, how long would it take, how much longer would it take to perform an LU decomposition on a 3 by 3 matrix as compared to a 2 by 2, and moreover, how long would it take to perform this algorithm on a 100 by 100 matrix, or even 1,000 or greater. So let's first work with this 2 by 2 matrix and figure out how we can get A into the form of an upper diagonal matrix by getting that lower left value, that number 8, how we can set it to 0. To begin, let's multiply this first row by 8 over 4, or multiply it by 2 effectively. And what that leaves us with is 8, 20, 8, and 1. And then let's subtract the first row from the second row. And after we do that, we'll store it in the second row and leave the first row as we originally had it. So the original first row is 4 and 10, and in the second row is 8 minus 8 and 1 minus 20. That leaves us with 4, 10, 0, and negative 19. This is equal to the upper diagonal matrix U. The lower diagonal matrix consists of all the factors that we've used to eliminate different terms. So for example, we eliminated this term, which is A2, 1. So this 8 over 4 will go into this lower left location for L. So L will equal 1, 0, 8 over 4, or 2, and 1. If we did this right, the product of L and U, the matrix multiplication, ought to equal our original matrix A. To check that, I've written out L and U, and to do the matrix multiplication, we'll first multiply that row, take the product of that row and that column, which is equal to 1 times 4 plus 0 times 0. We'll store that in the upper left. And in the lower left will be 2 times 4 plus 1 times 0, or 8 in the lower left. We can do a similar thing for the upper right and the lower right values. Here we've got 1 times 10 plus 0 times negative 19. And finally, we've got 2 times 10 plus 1 times negative 19, which of course is equal to 1. And indeed, we've come back to our original matrix, and it looks like we've done the LU decomposition correctly for this one. So let's figure out how computationally intense that was. So we'll calculate the number of floating point operations, or we call them flops. The first thing I did was multiply row 1 by 8 over 4. And it took one floating point operation to compute 8 over 4. And it required one floating point operation to change this one value, A12, or this number 10. Note that there was no need to change A11. I did it here for clarity, but we're going to come back and we'll end up with that same value anyway, so we don't need to waste computational time to change that. The next step was to subtract the first row from the second row and store that in row number 2. Somewhat surprisingly, it only required one flop to make this subtraction. We already know that A21 is going to equal 0 if we did it correctly, so really the only floating point operation we had to make was 1 minus 20. So what this says is for a 2 by 2 matrix, we could say n equals 2. It required 3 flops to perform this operation. So there are 3 floating point operations to complete the LU decomposition for n equals 2. So let's go through a matrix where n is equal to 3. It's a 3 by 3 matrix. And we'll need to compute 9 different values for the upper and the lower diagonal matrices. To begin, let's multiply the first row by 10 divided by negative 7, which will switch this negative 7 to a 10, 0 to a 0, and we'll get 2.8571 for the upper right. It required one floating point operation to compute 10 divided by negative 7, but only 2 flops to scale the first row. And really all I really need to change are these 2 values. I changed the first one just for clarity. The second step is to compute the difference between row 2 and row 1, and we'll store that in row 2. It requires 2 floating point operations to make this subtraction. Again, there's no need to subtract the first column since A21 is going to be equal to 0, so the 2 calculations we needed to make would involve this variable and that variable. As a third step, let's multiply row 1 by 10 divided by -7 again. We'll store that as L31. It again took one floating point operation to compute 10 divided by -7, and two floating point operations to change that variable and this variable. So we'll subtract row number 1 from row number 3 and store that in row number 3. And it only took two floating point operations to accomplish this. Finally, we need to make this -8 equal to 0, so in the last step, we'll multiply row 2 by -8 over 6, and it will compute, it takes one floating point operation to compute that, and only one flop to scale row number 2. So this is the only number I really had to change to make this happen. Then lastly, let's subtract row number 2 from row number 3. What's interesting is that this only required one floating point operation to change that last value. This is my upper diagonal matrix. I've got zeros in the lower left. And my lower diagonal matrix is just the lower diagonal of those factors that we computed. And these are the three factors we used to scale rows 2 and 3. And when I compute those, this is what I come up with for the lower diagonal matrix. To check to make sure we did everything right, let's again multiply L and U, and we should come up with the original matrix A, which we do. So to compute the number of floating point operations we needed, let's tally them up. Step 1, we've got 3, 4, 5, 6, 7, 8, 9, 10 flops, 11, 12, and finally 13 floating point operations to make this happen. So if I was to start making a table, let's choose n as 2 and n of 3. The number of floating point operations is equal to 3 for n equals 2, but then it jumps up to 13 for n equals 3. So what we see is a dramatic increase in the computational time when n is increased from 2 to only 3. And you can imagine how many floating point operations are required for a matrix, a much larger matrix. And we'll look into that in the subsequent screencast.